Okay, let's get started with Chapter 3, Section 4, Derivatives of Exponential and Logarithmic Functions. In this section and series of videos, we will learn the derivative of the function e to the x, the derivative of the function a to the x, the derivative of the natural log of x, the derivative of log base a of x, and then we're going to extend that power rule that we've been talking about for so long to make it applicable for any exponential real number power. But we're beginning this video with the derivative of e to the x. So there's only going to be that rule, no new vocabulary in this section, and let's get started with this. Way back in chapter 0, our review chapter, we looked at y equals e to the x, and we said this function has so much use in modeling exponential growth, and it's going to be a big one for us here in calculus. So first of all, let's talk about the number e. We defined it as a limit of 1 plus 1 over x to the power of x as x went to infinity. In other words, e was equal to the limit as x approached infinity of 1 plus 1 over x to the power of x. And this is approximately 2.718. It is a number that goes on to infinity as far as its decimal places go, but 2.718 is about all we'll ever need. And there was a result having to do with limits and e that is going to be pretty interesting for us in this particular section. And it's this right here, that the limit as h approaches 0 of e to the h minus 1 over h is equal to 1. This is so interesting because it has a direct application to the derivative of e to the x. And that's where our focus is in this video, the derivative of e to the x. And on the next slide, we're going to develop that derivative. So let's begin this way. We want to find the derivative with respect to x of the function e to the x, and we begin it with a limit definition of derivative. The limit as h approaches 0. Here's f of x plus h. That's e to the power of x plus h minus f of x itself, which is e to the x all over h. This is f of x plus h minus f of x. Over here to the right is a proof of that limit that we talked about on the last slide. This is the limit as h approaches 0 of e to the h minus 1 over h. And as we can see from the TI-84 screenshot here, as x approaches 0 from both sides, this function approaches 1. So let's keep that in mind and then come back over here to our development of the derivative and see where we go from this. So let's see, e to the x plus h and e to the x. I'm going to separate the first term. So this is going to look like limit as h approaches 0 of e to the x times e to the h minus e to the x all over h. We can do that because of exponent properties. Then, since the first term and second term in the numerator both share an e to the x, we can factor that out. So this becomes the limit as h approaches 0 of e to the x factored out. That leaves e to the h minus a 1. And then this is all over h. Let's look at that e to the x factor again. Because it is an e and it is to the power of an x, and neither of those are h's, which is the limit variable, that can be factored out and dealt with on its own. So we'll take the e to the x, factor it out, and now we're multiplying by a limit as h approaches 0 of e to the h minus 1 over h. And hey, that's that interesting result. This limit is this graph to the right. And we know by graphics and by table form, this is 1. So we can replace that with 1 in this derivative development. So now we have e to the x times 1. And this result says that the derivative with respect to x of the function e to the x is itself. I'm going to write it here because that's so interesting. The derivative of e to the x is e to the x. It's the derivative of itself. So let's see that more formally then. The derivative of the function e to the x is itself d dx of e to the x is e to the x. And if u is a differentiable function of x, so we're getting in the chain rule here, the derivative with respect to x of e to the u is itself e to the u times du dx, or some students like to remember this as simply u prime e to the u. So it's the chain rule with e to the x. Well, let's get an example here. Find dy dx if y is equal to e to the power of x plus x squared. So dy dx is, okay, it's an e function. It's the derivative is itself. So e to the x plus x squared. Now let's invoke the chain rule, times du dx. Well, the u in this case is x plus x squared. So times the derivative of that with respect to x would be 1 plus 2x. And we can write that without the little dot multiplier. So x plus x squared, we'll put that in parentheses, times 1 plus 2x, and we have it. There's our derivative. Now, let's try exercise 9 from the text. In exercises for this section 1 through 28, we just want to find dy dx. So here's y defined as e to the power of the square root of x. So dy dx will be, first of all, itself, e to the square root of x power, times now the derivative of that exponent. The exponent is the u, so we can even make a note of that here. Whatever's in that exponent of the e will always be the u. So now we want to do times the du dx. Well, the derivative of root x is going to be 1/2 x to the power of negative 1/2. So this should simplify then to an e to the root x power in the numerator, and then a 2 root x in the denominator. And we have our derivative, and that's the derivative of e to the x.